work with make. So I'm going to be talking about make. I'm going to say some things towards the end that give you context for other build systems, because in the end they all do the same thing. What are build systems and what are their goals? So build systems goals are, at the very least, to kind of organize the magic incantations that you have to use to essentially build your code. So they automate the compilation and linking of source code into your final executables, right? For different systems, they may do different things. XV6 not only produces the executables, but also allows you with a QEMU option to be able to run the virtual machine. So, they can do a lot of other things, but at their core, they're there to automate a lot of this build process. Two, and that's really important, right? I mean, if you're on a big team of developers, you better all be sure that you're building the source code in the same way. If a new developer jumps onto a project, they need to be able to know how to actually run your code, right? This is a really, really important thing. Second, build systems are there to make sure that the compilation is only done on things that they need to compile. So you do not need to recompile all code, all files when you build a system. You actually only need to recompile the files that have been changed or that rely on files that have been changed. So build systems are there to automate that process. And they're there to actually make the build system easier, which is to say, when you're actually writing all these instructions for how to actually build your system, they aim to be a programming language to make it a little bit easier to actually write that build system. So I have created a few examples to motivate build systems and to motivate everything that we're talking about here. And I do want to remind you before we go on to that that is absolutely the wrong Firefox, and I do not know why it's choosing that. Hold on one second. For some reason it defaulted to the bad Firefox. There we go. Okay. I want to remind you that all of this is in a repo for the Evening OS Hour on my account. So I always populate everything before this. So if you want to follow along with everything that we're doing, you can do so. So you can see the actual rendered markdown for what I'm going through in Emacs is here. So just a brief reminder there. Okay. So the first example is I created what I think a lot of people would do intuitively if they were told, hey, somehow you need to organize the magical incantations that build your executables. And that is to just generate a build script, literally a shell script that includes all of the information that you'd want to have to actually build your program, right? So let's look at what that looks like. So let's go into the build script version of this, and I've written a build script. That build script just includes a number of commands that literally build my project, right? So what is my project? Let's dive into that a little bit first. So I have x.c, y.c, and a header file, z.h. So I have x.c, y.c, and let's split this not that way. Ugh, let's not do any of that. That's what I wanted. X.c and z.h. Okay. Let me reemphasize that when we see the build.sh, an sh file is a shell script. So it's literally interpreted by your shell to just be a set of commands. So in this case, it'll execute GCC, GCC, and GCC. And the hash bang at the top just says, run this file through the shell, right? Okay, so this program is just a few things. One, in y.c, we include a single library function, y function, and it just returns kind of a dumb value. The argument times some constant value. And we can see that constant value is defined within z.h, a header file that is included from y.h, and it's 42 because that's, you know, the meaning of life and everything that you'd possibly need. We have the prototype for the function, fine. And then x is kind of our main file. It includes an x function that calls the y function with an argument. It includes z.h so that we can figure out what the prototype of the y function is. And as a main that simply calls this x function, prints out the value, and then returns. So this is a trivial program. Nothing's really here, right? This is not interesting in any way. However, what I do want to point out is that if either x.c or y.c are changed when I'm building my system, I probably need to rebuild that .c file and then recompile it executable, because not only have I generated a new .o file corresponding to list.c file, but I need to, you know, compile all of the .o files together to generate the actual output. So looking at this running so that you see what I'm talking about, if we run the build system, it executes, and all that it did is run all of these commands. Some of them generate the .o files, so we see that x.o and y.o have been created, and then the final GCC command there generates the binary, compiles together the .o files. So if I were to modify either of the .c files, you know I absolutely have to rebuild them, right? However, the tricky part is that if I modify the .h file, well, I'm also still going to need to recompile both of my .c files because they both include .h. They have a dependency on it, right? This build system, all that I've done is I've encoded the commands for building the system into this shell script. That's it. It has no intelligence about only recompiling specific files if they need to be recompiled, right? So for instance, if I were to take my y.c function and change it to be that I want to return a +1 times the constant, right? Okay, cool. Now I know I need to recompile my y.c, but I actually don't need to recompile my x.c because it didn't get modified. The .o file is going to be exactly identical to what it was before. However, of course, if I run my build script, it runs all of the commands. So to show that, let's remove all of the o files, and yeah, it's going to, oh my god, run all of the commands, regenerate all of the .c files, etc., right? I will answer that ask at the very end after I'm done talking about this. Okay, so this is all very simple. I have my bin, it runs the code, it's fine. Okay, let's go back to what I said build systems are for. Build systems are to organize the magical incantations that you need to build the system. Cool, that's what our build script does. However, it doesn't only recompile what's necessary to recompile because it's been modified, and it certainly doesn't contain anything to make writing the build system easier. Every single command that I wrote, every single command that I had to write within build.sh, I kind of have a lot of repetitive stuff here, right? So I'm repeating myself a lot. What happens if now I want to add optimization flags? Okay, now I need to go through and add O3 to all of these lines manually, right? That's not great. That's a recipe for forgetting to do it somewhere and having horrible bugs. So this is not a great programming environment for a build environment. So nobody does this. This is not the way that you actually do build systems, right? So now, also, if I want to get rid of all of the crap that was generated by the system, I kind of have to manually go through and do the commands to do it. Okay, that's not great. So that's why we have Makefiles, because Makefiles allow us to more easily write our build system, and they allow us to only conditionally compile what needs to be recompiled because it's been modified. So xv6 is a relatively small system. If you type make clean and then make, it rebuilds every single .c file, and it does it pretty quickly. But the Linux kernel takes 4 hours to recompile if you go through everything, right? So you really only want to have to recompile the .c files that you changed, right? So Makefiles try to solve that problem. So let's look at a simple Makefile in this directory. So this is very similar to some of the Makefiles that I provided for you for the C programs that were earlier in the class, right? These are the C programs for the linked list and all of that stuff, right? Okay, so what do we have here? First, we have the ability to define variables. Variables allow us to not have to repeat ourselves, right? So here I'm saying I want to use whatever I've set the CC, the compiler variable, to, and I want to use it again here. So I know that whatever my compiler is set to, it will be replicated in these two places. That means if I want to change this to the LVM CC, the LVM compiler, now I just need to change this one line to do so. So I don't need to go through my entire program and change that, right? So variables are useful just like they're useful in programming, right? Likewise, my C flags, these are all the flags that I end up passing to GCC when I compile a C file. As you can see here, they're placed on the command line for building the C file. If I wanted to now add my optimization flags, I've even defined a nice variable called opt for those optimization flags, and I can pass 3. Cool, now it's getting much faster because I'm optimizing the code even more, right? I don't need to go through and modify a whole bunch of lines, adding the optimizations manually, right? I can summarize all of the C files in my project in a variable. I can summarize all of the objects that I want to generate for those C files in a variable as well. And I can summarize the binary, right? So variables are intrinsic in Make. They're important for documenting your build system, for documenting your Makefiles, and they're important for just making it so that you don't need to repeat yourself. Okay, now the fundamental form that we always abide by in a Makefile is this. Something on the left. So each of these lines and the incantations below them. So for instance, this is a build rule. Every single rule starts with this colon delimited separation of the target, the thing that is going to be built, in this case all, which actually isn't building anything, and the dependencies that has to be complete and to be able to execute. So it's kind of convention that all Makefiles include a all rule or an all directive so that you can type make all and it will build everything in the system. It's also convention that you tend to provide a clean, as you now know from xv6, right? So clean just kind of gets rid of all of the build artifacts within your system, right? So in this case, it removes the binary and all of the .o files that were generated. Actually, this is not using the abstraction that we came up with, so it should be that. That's cleaner. Remove the objects. We defined a variable for that for a reason, right? So let's look at this. What is this rule within GCC saying? It's saying there's a binary. That binary ends up being bin, which is the output that we actually want to generate. It's the final binary that we can actually execute, the program that we want to execute, right? It depends on all of the .o files having been properly generated in the system. So it's saying, for this rule, this command to execute, I absolutely require that all of the .o files have properly been created within the system. So again, to the left of the colon, if you want to build this, then all of these things need to have been created. And variables in Make, it's just kind of copying and pasting. this stuff there. So this is functionally equivalent to just having that, right? But of course we have variables, so why not use them, right? Okay, so that's what each of these is saying. Now let's kind of demystify that a little bit. So what I'm saying here is all, if I want to build anything, if I want to build everything, then the binary must be prepared. Oh, well, okay. How's the binary prepared? Here, the binary is prepared because it's the target on the left-hand side of the rule. That depends on all the objects having been prepared. Oh, okay. Is there a rule for creating the objects? It doesn't seem like there is, because all of the .o's, like there's no x.o rule. So I would think that would look like x.o is dependent on, for instance, x.c, and then I could write some stuff there, right? And I actually do have that rule. It is this rule. So this is a make feature where we essentially have wildcards. We essentially have regular expressions, where the % is a wildcard. So it's kind of anything, right? So this is essentially saying if you want to build any text .o, then that depends on that same text .c. So if I want to build x.o, so there's a dependency on x.o, well, to generate x.o, that's going to depend on x.c. Oh, okay. So this is actually a generic rule that applies to every single .c file that will generate a .o file. So when you want to create a .o, this is what does it, right? And what is this doing? It's essentially saying run GCC with the flags that I've set. And here we have a couple of make special variables. At says whatever is on the left-hand side of the colon. The target, just basically take that and copy and paste it there. Okay. The caret says take whatever is here on the right-hand side of the colon and paste it there. Okay, so that's basically the rule for creating a .o file. So we've said within this rule here, this is how you generate, this is the recipe for generating a generic .o file. It depends on the .c file, and here's the way that we build that .o file from the .c. And we're essentially using these to reference the specific target and dependencies above. Okay, so let's see that actually running. If I run this, I can see that it actually works, and I have, let me actually run it in here. Okay, make clean, make. So I can see that I have one GCC running. So I know that that variable is working out okay. And then I have a whole bunch of flags that are being passed to the GCC, which is correct. I have my GCC, and then I have my flags, right? And then the rest of it, I have my -c, that's just getting translated directly. I have my -o, that's being translated directly. But now I can see it's actually putting the x.o and the x.c into those proper locations. It's replacing the $@ with the .o and the $caret with the .c, right? Okay, so if we have 3 test files, for example, the .v extension, and want to only run one, how do we do it with this Makefile? So this is running this rule multiple times, once for each .o file that it's asked to generate. And that's because we are separately listing our .o files here. So when it sees the dependency over here on x.o, at that point, it will look for the rule to actually execute for that, and we'll see, oh, I know how to generate that .o, I'll do it here, right? And then it will get to the next dependency, y.o, and it will say, oh, same rule. I can apply this and it will generate my y.o, right? So that's how this actually ends up getting run once for every single C file. And that's kind of the beauty here. That's the point that I want to make, right? This is making the build system easier to write because I don't need to write a command for every single .c file. Instead, I write a command for all .c files. I write a generic recipe, right? So hopefully that answers the question. If not, please continue to ask. So just a reminder, what the @ does here is the $@ is shorthand for the target that is on the left-hand side of the colon. So whatever is on the left-hand side of the colon here gets replaced where this @ is, essentially, right? Okay, so now to clarify also, after we build all the objects, this is the rule that we use to build all the objects, right? The objects themselves are not runnable, okay? So I cannot do a x.o. That's an object file. It's not a executable file. Let's see what file says. So this is, nah, I don't want to go into that. Okay. So after all the objects are created, then the dependencies for this binary rule are satisfied. So after the objects are created, then binary can be generated. How do we generate binary? By running this command, right? So what is this running? It's saying run GCC, and the output of running GCC should be the name of the binary, in this case bin, and it should take as its arguments all of those object files. So remember, $caret is all of the things on the right hand side of the colon, which in this case is all of the objects. So what does that look like? Well, we see that we have this GCC o bin x and y.o. So we're actually combining our .o's into the binary, and the binary is the thing that we can actually run here, right? So hopefully that explains. And taking the explanation all the way through, once binary is created, then we can actually execute the rest of the rule for all, but there actually isn't any code to execute for all that's within the rule. So we're done. Second thing that I want to point out is we have this all rule up top. The reason that we kind of, by convention, have all at the top is because when you just type make, it always just by default runs the first rule in the file. So we don't actually need to type make all. Make all is the same as typing make. Now notice that when I type make now, it actually doesn't build anything. So there's nothing getting run here. So if I execute my bin, cool. I don't need to build anything else. I don't need to build anything here because I haven't changed any of the files. If I don't change any of the C files, why would I possibly need to rebuild the binary, right? So if we have test1, test2, test3, all.c, and we want to execute the binary for only test1.c, how do we do it? Generally, you don't have that case. You might have, if you do have that case, you might have a separate directory with a separate make file for each of the binaries that you want to generate. This can get more complicated. We could have this binary thing, we could have it only run on a subset of the files, or have multiple lines of code here that generate multiple binaries from different subset of the objects. You know, there are many ways that this can happen. But in this example, we are generating one binary from all of the .o's and .c's. I want you to understand not every way that you can use a makefile, because there are an infinite ways. This is a Turing-complete language. But I want you to understand how makefiles think and how they function, okay? So, a reminder, part of what build systems are there to do is to process only what's necessary, rebuild only what's necessary, right? So we're seeing here that when I type make, it says there's nothing to do. Again, that's because I haven't modified any of the files. If I were to remove the binary, well, okay, now I hope it'll rebuild the binary, right? Oh, it does. But importantly, It only ran the command to rebuild the binary. It did not run the command to remake the .o files, right? The .c, the x.c and the y.c didn't change. So the x.o and the y.o do not need to change, right? So all that we need to do is run the command now to regenerate the binary from the .o files, right? Make is being very intelligent here, and it's essentially saying, I will only run this rule on the .c files that have actually changed within the system. So if a .c file has not changed, then it will not run this command again, because the .o file would be exactly the same if it were to run again, right? Here, the binary did not exist anymore, so it knows it needs to run this rule again. So that's why make was smart enough to only run that second part where we're running the rule to regenerate the binary, right? Okay, so somebody's confused about the binary here versus the binary here. Everything, this is just an Emacs thing, right? So everything on the left-hand side of the colon in Emacs is the dark pink, because that's a target for the rule. The difference between this and this is just, this is like a shell script. When you want to use a variable, you have to, surround it with $sign and parentheses. When you want to declare a variable, you do not. So this is just how you declare variables and how you actually use the variables. That's all. Good question. I glossed over that. Okay. Now, if I were to go in to my y.c file and change this like I did in the previous example to a+1, so I'm just changing the logic for the y function, right? So the .o, the object corresponding list, the code generated for this, absolutely has to change, right? So I hope that this is going to actually rebuild the .o file for y.c. And when it does so, I hope that it will also rerun the command to generate the binary, because y.o will have changed, okay? So when I run make now, it says, the y.c that you had has now changed. You modified that code. Because of that, I need to regenerate the y.o. I need to rerun this command to generate the y.o. And then, because the y.o has changed, it knows that it needs to rerun this command to reproduce the binary. So all that make is doing here is it is looking at, it is looking at what has been changed within these dependency lists, and it's rerunning the command for those. And it does it, in this case, transitively, so that if we regenerated the .o, then we know that that's in the dependency list for the binary, so we need to also regenerate the binary. So this is that second main thing that build systems are there to do, which is only rebuild files that it needs to because the source had changed in some way, right? So I just want to be clear here. If I were to, this line, it's using variables, it's doing all of this, right? So it's using the features of make to make it look pretty. That would be equivalent, if I were to manually write it all out, to GCC zero, include directory, that's I there, and then this is actually the simple version. I don't need any of this. making life more difficult on myself. So O for bin and x.o, y.o. So this right here is equivalent to lists. But this that I have highlighted right now is using variables, so I could actually change them at one point in this file, and it'll change the behavior at multiple points throughout this program, right? So for instance, if I were to modify objects and add a third file, so let's say I added another file into my program, I add it there, and then all of a sudden this command automatically works, right? I don't need to change anywhere else. If I were to manually write all of this out, then all of a sudden I need to start changing everywhere where that's required, right? So you use variables in programming languages and in general to reduce redundancy and make your programming life a lot easier, right? And that's what we're doing here. Okay, so this is a simple Makefile. It's nice because it provides a recipe for compiling any C file into a .o file. It's nice because it does selective compilation of only those things that are required. So if we were to run make here, we don't need to do anything. If we were to, again, let's modify this time x.c. So I'm going to modify it really stupidly by basically making a no-op change. So if I make that change, then cool, I know that I need to recompile X because I modified it. And I know that I need to regenerate the binary because I modified X, right? Make is smart enough to only do the compilation jobs that it needs to and nothing more. Again, in very, very large code bases that can take tens of minutes to multiple hours to compile, this is immensely useful, right? You don't want to wait for 4 hours to compile your program. You just want to wait for the 2 seconds to compile only the things that you changed, right? This is what build systems are there to do, right? Okay, so that's an example of a relatively simple build system. However, there still is a big problem with this. So the big problem is that what if I take my z.h, which I know is a header file, and I want to change the constant. I want to change the logic within it to be something else. Now, I remember that y has this constant that I just changed. So I know that y.c should recompile now that I've changed the .h file, right? I know that it has to because I've changed the logic in it, right? So if y.h should recompile because I changed z.h, wait a second, it doesn't happen. So here the problem is that make doesn't understand that there's a dependency essentially between y.c and z.h. It doesn't understand that because it doesn't understand C. It doesn't understand our programming language. The dependency comes from our programming language. And within our happy Makefile that I can't access because Emacs is trying to be too smart, there's no dependency here, right? There's no way that I'm saying to generate the .o file for y.o. Yes, it depends on my y.c, but also it depends on z.h. There's no code here for that, right? If I were to add the code and explicitly modify it in this way, then all of a sudden it will vomit because of a reason that I don't want to go into next. Never mind. I'm going to delay the discussion of that. Long story short, this Makefile is great, and it will rebuild files when we modify them, but only the .c files. It doesn't understand within my .c files the dependencies because of the includes, right? So that's the core problem here, and we need some way to solve that. So I have a good build system, I have a powerful build system, I have something that generically will build a lot of C programs, but I don't have something that's maximally useful yet, right? So that takes us to the third example. So we've gone through a simple build script, a simple make file that allows us to do a whole bunch of things, and now we're going to look at a featureful Makefile. I want to show actually the text for that. So I was writing this and was writing this like half an hour ago, and I realized as I named this to a featureful Makefile that every single time I read it, I just read a fearful Makefile, and it's painful how true that actually is. But regardless, it is a featureful Makefile, so we'll stick with that, right? So this actually is exercising a lot of the really cool features of Make that kind of take it from just being kind of a niche thing to being a full-formed build system, right? And this example is going to show how we actually kind of take our Makefiles and we can kind of integrate them with the surrounding shell and with the surrounding environment. So I'm going to go into my featureful build system, and I've complicated things a little bit. So I have my Makefile, but I only have my x.c in here, and let's imagine that y.c is actually a kind of library for my project. So now I have my library directory with y.c in it, and then I have my include file, the z.h, in a separate include directory. So I've organized the structure of my program a little bit, right? So one, I want to solve the problem where, I really want Make to understand these dependencies encoded in the include directives in my actual C program, so that when I modify a .h file, it will recompile the C programs correctly, right? I really want that to work. Without that, you can't really use Makefiles with C properly, right? So let's look at this improved, yet unfortunately a little complicated take on Make. First thing is that I want you to look at these first 3 lines. I've written this Makefile in such a way that, given some assumptions, these are essentially the only 3 lines of code that you would need to change if you wanted to create your own program, your own set of C files, .h files, and all of that, and you wanted to be able to distribute the C files across multiple directories. You wanted to have an include directory. You could have as many C files as you want. You can have whatever, and these are the only 3 lines that you would need to really modify for it to be able to work. So here what I'm specifying is where the directories that include our code are. So it's this current directory, and it's the library directory. We know it's library because, as I said, within the library directory, I have my y.c in this version of the program, right? And then my include directory, look in the current directory in case I put a .h file here, and then also certainly look in the actual include directory, right? So these are the 3 lines of code where it's like, you just need to say where your code is, and the Makefile does everything else. So this kind of is going to show a lot of the power of Make. So I have my CC, I have my variables defining things within the system. I added this new set of flags for dependencies. These are the way that GCC and C compilers allow us to work with the compiler, to allow Make to work with the compiler. What these are essentially telling GCC is, when you build the programs, don't just build the programs, also generate dependencies in a way that Make will understand, so that if I modify one of the .h files that this is dependent on, it will also rebuild the C program. So this is kind of a magical incantation that we use and pass to the C compiler to magically work with Make. Okay, so now my C flags include not just the normal stuff, but also the dependencies. Okay, now we're going to get to the first weird part of Makefiles. Makefiles are incomplete, they have loops. Here we have a for loop. So within a for loop, here what I'm saying is create a variable d for each iteration of the for loop, iterate through all of the include directories. The include directories are, again, all of the directories up here that I want to look for include files in. And for each of those Ds, with those directories within that list of include directories, generate a capital -I and then the name of that include directory. So all that this is doing is essentially generating something that looks like I that, and then I include. So you can see my include directories up here are first this directory and then include. This for loop is just going through each of those and prepending -I onto each of them. So this, the output of this for each loop right here, is essentially just going to be exactly this, right? So it's just adding the include directories into the C flags, right? Somebody is asking if include is the name of the directory. There is no include here, so I don't. Oh yes, include is the name of the directory. Yes, thank you. So remember that I have this include directory here, right? So I know that my .h file is in that include directory, so yeah, I better include it within that incdir. Okay, now we want to find our C files. In the last Makefile, we kind of manually listed out all of our C files, right? That's fine, and there are some programs, some systems that do that. XV6 absolutely does this, right? So some C programs will do that. However, we're trying to automate this. We're trying to make this a nice environment to use. So what we're going to do is we're again going to use our iteration. This time we're going to iterate through all of the directories within our code dirs, right? So that's going to include our library directory and the current directory. So we're essentially saying that the current directory includes my x.c. It might include other C files, I don't know. And my lib directory also includes .c files. So I want to go through all of those and treat every C file within that as a C file that I can track within this variable. So I'm iterating through all of those code directories, the current directory and lib. For each of those, I'm kind of setting a variable equal to d for that iteration, and I'm using this wildcard thing. Wildcard essentially just says, yeah, so within that directory, it might be this current directory dot, or it might be lib. Find all of the clean star .c things, right? So find all of the files that essentially end with .c. We know that those are C files, and it'll list all of those out, right? So all that this is doing is essentially creating a list. If we were to expand this out, C files would essentially be equal to, let's see, would be x.c and lib y.c. So let's see that. So I know x.c is in the current directory, and within the lib directory I have y.c. So this is just programmatic code for essentially generating this list. So it's just every .c file that I have, right? Cool. So now I have a programmatic way for finding all of the .c directories. All that I needed to say was essentially what directories to look in, right? And this is really powerful because now when I'm developing my program, when I'm developing my code, I can add in these .c directories, my C files. I can add in new ones, remove them, and I never need to modify my Makefile. It just automatically finds all of the C files for me, builds them properly, and I don't need to worry about it. A good build system, after it's properly created, just kind of gets out of the way, right? Is there a way to programmatically recurse into subdirectories, assuming we have subdirectories in include or lib? There is. I'm not going to go into it because we're getting into even more complicated things. One thing that I should list related to that, but a little bit more roundabout, is that within a Makefile, within a rule, so I have my all again, I could actually call make within a subdirectory. So if I had a Makefile defined in the lib directory, this would actually recurse into the library directory and call make there. So there are ways to kind of recurse and do a whole bunch of stuff in a complicated program, in a complicated project, and they are used in a lot of complicated projects. I'm not going to go as much into them right now, but a lot of them include that, kind of just calling Makefiles within the subdirectories. Okay, the next kind of tool that we have in our Makefile belt is pattern substitution within strings. So I've generated my list of C files now, and now what I'd like to do is generate my objects, right? My objects are the .o files. So all that this does, I have my pattern substitution tool within Make, and all that that's doing is for all of within the C files. C files is a list of all of my C files. So for each of those items within the list, take anything that matches something.c, and of course they're all C files. I only looked for things that match something.c, right? So that's going to match all of them. Convert that into that something.o. So that's going to convert all of my C files into the .os. So I'm going to now have x.o and lib.y.o. So this is just replacing all of those previous .c's that were right here with .os. So it's programmatically generating all of my .os. Those are the .os that are going to be created by the build system. And then the way that Make works with GCC, with the C compiler, to generate the dependencies is so again, let me reiterate. Within my C programs, I have these includes, right? That says that there's a dependency on the .h. If the .h changes, I better recompile this file, right? The way that GCC does that is certainly, as I said, you pass in these flags and it'll kind of do it magically for you. But the way that it does it is it generates .d files. So this is all of those .d files. Instead of replacing and finding all of the .os, all of the object files, I'm just creating .d files. It's kind of unimportant what's happening there. I'm not going to explain in dependencies in great detail. I'm giving you a pattern to follow that will work. This code is exactly the same as we had it before. This is a default rule that is executed. It relies on the binary. The binary relies on all the objects. I've now programmatically generated all those objects, which is pretty awesome. And I have kind of that same rule as I had before for essentially saying, yeah, compile a binary from all of the objects. So that's cool. And because I have this dependency on all of the .o files, the .o files are going to come here and say, well, I know how to generate .o files. It depends on the .c files. When I depend on the .c files, I have kind of this same rule for essentially generating the compiler directive for compiling them, right? So I actually kind of have really the same thing as I had before, where if I build, it just kind of generates the same commands. The only difference here is that I am generating the .o file in the library directory because I've moved my y.c into the library directory. That's fine. And I've kind of now including this include directory in my list of the include directories, where when I do a pound include, it will look in that directory to see if the .h file is there, right? So everything's kind of the same here, right? It's kind of generated the .os just the same. It's also generated a .d file here. Again, that .d file somehow works with the make file to kind of say, hey, make, when this .c file is looked at, you better look at all the H files that are included in it. Somehow that x.d includes that information about which .h files the x.c depends on, right? So again, if I were to remove the binary, cool, it just needs to run the last command to generate the binary from the .o files. If I were to modify the x.c function, or sorry, C file, then it has to rebuild the x.c. Cool, great. But now, because I've included all of this information, I've included for the dependencies, I basically pass these magical flags to Make that magically generates the .d files. Now Make, if I were to touch the, where is it? It's include z.h, include z.h, and I were to change this to 43. Now I've changed the z.h. Let's include it in both y.c and in x.c. So I know that they both better recompile. Now it actually works correctly, and they do both recompile. Now that I've compiled everything, it doesn't need to do anything again. If I were to touch anything, it's only going to recompile the corresponding things that need to be recompiled, right? So this is what Make does, right? And this is what complicated Makefiles can actually do. There's one last thing that I want to go over before we kind of terminate. This is the example of how we actually use the dependencies. I'm not, again, not to go into how Make interacts with that or what the .d files do. This is just kind of the magical thing that you have to do to make it work. You can read more online. But I want to also note that Makefiles are really cool because they're basically kind of the magic of shell scripts combined with all this logic about what to build and all these variables and all these cool things, right? Because if I do a make diff here, I've added a rule to essentially call Git. And to call Git to get some cool information about changes that I've actually made within my program in the meantime, right? So let's look at what that says. Well, Git Status tells me what files have been modified, and more importantly, more usefully, what files are untracked. If I forget to, add a .c file into my to add it into Git, then this will remind me, right? So I really want to do this always before I do a push, and I just want to often say, well, okay, are the files that have been modified the ones that I think are modified? So this is just a sanity check for me. I like running Git stat to get this information, but then I'm also running Git diff stat, which gives me a summary of which files have been modified and how they've been modified. So readme.md, I've added 37 lines to it. Feature or z.h, I've added 2 lines. I've added a line and removed a line, right? So I've changed 1 line, essentially. So this is just a useful thing. This is equivalent to saying git diff stat. It gives me the same information, right? But now I've created a Makefile command that will essentially do it all for me. Further, I didn't want it to print out the fact that I was calling Git Status. So, oops. When I call make diff, I don't see the lines where it basically would have said git diff stat. I don't see that line here. So in Makefiles, you can actually use this @ symbol before a line to essentially say, do not output this line onto the console. Run the command, but don't print out the command. You can also see that at the top of this, I have kind of added this note, the status of the repository and the volume of per file changes. So this is just something that I wanted to output at the top of kind of this git diff stuff. So you have the info command that you can use to essentially output something when this rule is actually executed, right? So you can do really powerful things with this. You can write rules that help you automate many of the common tasks that you might want to run within your repository. So another one of these that I've added is Git Distribute. If you want to distribute your code in a binary format to people, then, oops, no, it's not Git, it's Make. Duh. So what I've done here is I just have made a make rule for actually creating a tarball for my entire repository. So now you can see there's this dis.tgz that's been created that includes all of my code, right? So that's great. And you can see that that was just a simple rule here. Create the distribute rule. Definitely clean the directory before distribute runs. I don't want to distribute all the .o files and the binary, and then just run the tar command to zip up and put into the dis.tgz file all of my files, right? So point being, make is a powerful thing, and it can really automate not just the building of code, but also some of the common tasks that you perform within your repository. And the notion of dependencies is a generally useful thing. We've seen how dependencies are absolutely necessary so that we only recompile what needs to be recompiled, i.e. only when I change the .c file do I actually need to recompile this. But we've also seen here with distribute that I will want to run my tar command here, but before I run the tar file, I want to make sure that I've removed all of the intermediate .o and binary files. So I just add a dependency layer. I don't need to run the rm again to do all of that, right? So I don't need to type all of this out again, redundancy. No, I just say, yeah, run clean before you run distribute, right? Yeah. So anyway, that's all that I really have for this. That's all that I have about Makefiles. I should actually make it so that I remove the distribution stuff when I run make clean as well, but I have not. So let me make diff. What changes have I made? Those all seem like good changes. Now I will commit. What is today? 10/2/19. Post make modifications. Cool. I looked at what I've changed before I actually did my commit, and now I'm ready to do my push, right? So that's essentially all that I had to go over for today. But before I stop, there was a question generally about something else before I got into Make. So certainly if you have any questions about Make, for those of you who are left, feel free to ask. But otherwise, that's all I have. Oh, okay, yeah, I'll go into the infinite loop thing. Okay, so I'll let you queue up any questions that you may have about this, and then I'll just quickly answer one of the other questions that somebody had. So there's a question more generally about what the heck this is. That's just annoying C syntax for essentially that. It's just an infinite loop, that's all. Do I have any make resources to suggest? Let me go back to README. I actually don't. Honestly, Make is a little too old and I've never found good resources. The best resources that I've found on Make are just other build systems, other Makefiles. And honestly, most of the useful stuff in Make, I've gone over. To be honest, I don't think that the other stuff is kind of a higher order bit. Once you get adept at using some of the stuff that I pointed out here, then reading through the Make manuals, you'll find what you need. You kind of look through the commands and there it is, right? But I don't know of any good resources, I apologize. So Make is a very old build system. Certainly newer build systems exist. Make is exceedingly powerful. It's the most powerful build system that I know of, but usually with power comes a lot of options. options mean that you have to write a lot of code within the build system to do things, right? So a lot of more modern build systems make more assumptions about what the build system needs to do and don't let you quite do as much. So it makes it easier to read and modify the build system because they're often less powerful. However, there are a lot of different build systems that have many different constraints. So autoconf is another old build system that actually is a build system for build systems. It generates Makefiles based on your system configuration. So if you're writing software in C or C++ and you rely on some libraries, autoconf is a great way to basically generate code corresponding to what libraries are present on the system or not. Ant and Maven are popular build systems for Java. They have a lot of the same primitives that we've gone over here with Make. Wildcard completion, dependencies, targets, all of that stuff. Ninja is interesting because it is a build system that's both not as powerful as Make and kind of horrible to use in the same way as Make. Like there's a lot of verbose stuff that's there. And that's because Ninja is supposed to be an output from a build system. So it's supposed to be a it focuses on being fast 100%. Make is actually not that fast because you're running a whole bunch of shell commands when you're doing a whole bunch of these rules. Ninja is meant to be very fast, but it's not as feature rich. But you have build systems that generate Ninja build systems. CMake is a cross-platform build system that, again, generates other build systems. So CMake is an example of a build system that actually generates Makefiles and Ninja scripts, if you want that, for you. But you do need to configure it, and it's a somewhat esoteric thing to do. And you can't do as much as you could do in Make. And there are many, many more. I include a list that you can find within this repository. So that's pretty much all that I have for the night, unless there are any other questions. So thank you all very much. Hopefully this gives you context. Build systems, they're one of those things that you never really want to learn, and you never really have a perfect time to learn it, but they are really important to learn. So hopefully this gives you a lot of pointers, and hopefully you can actually understand most of the XV6 build system at this point from what we talked about. It doesn't do much more than what I went over now. Good luck, enjoy the night, and I'll see you all in class tomorrow. Bye-bye.